Imagine a world where machines don't just process data, but understand it, where neural networks don't just recognize patterns, but reason about them. This isn't science fiction. It's the cutting edge of AI research today. But how do these systems actually work? What's driving the breakthroughs in natural language processing, computer vision, and reinforcement learning? Let's peel back the layers and explore the technical heart of modern AI. Section 1. The architecture of modern neural networks. At the core of today's AI systems lies the neural network, a mathematical model inspired by the human brain. But this analogy is more than metaphorical. Each layer of a neural network functions like a neuron, processing inputs through weighted connections and activation functions. Take the transformer architecture, for instance. Unlike traditional recurrent neural networks, RNNs, that process data sequentially, transformers use self-attention mechanisms to weigh the significance of every input element simultaneously. This allows models like GPT-4 or BERT to capture long-range dependencies in text, a critical leap forward in natural language understanding. But that's where it gets technical. The self-attention mechanism computes queries, keys, and values for each token in a sequence. The dot product of queries and keys determines attention scores, which are then normalized using softmax. These scores are multiplied by the corresponding values to produce a context-aware representation. This process, repeated across multiple attention heads, enables the model to focus on relevant parts of the input while discarding noise. Section 2. Training dynamics and optimization. Training these models isn't just about architecture, it's about optimization. Gradient descent, the workhorse of machine learning, adjusts weights to minimize a loss function. But modern AI relies on variants like AdamW, which combines adaptive learning rates with weight decay to prevent overfitting. The key innovation here is the use of mixed precision training, where models use both 16-bit and 32-bit floating point numbers. This reduces memory usage and accelerates computation without sacrificing accuracy. Another critical component is the learning rate schedule. Techniques like cosine decay or warm-up phases ensure the model doesn't overshoot optimal parameters during training. For example, in large-scale models, a linear warm-up phase gradually increases the learning rate from 0 to a peak value before decaying it, stabilizing training and improving convergence. Section 3. The role of data and scaling laws. AI models are only as good as the data they're trained on. But how do researchers determine the right balance between data quality and quantity? Enter the concept of scaling laws, empirical relationships that describe how model performance improves with more parameters, data, or compute. Recent studies show that, up to a point, doubling the data or parameters leads to roughly linear gains in performance. However, this isn't a free lunch. Training larger models requires exponentially more computational resources, raising questions about sustainability and efficiency. To address this, techniques like knowledge distillation are gaining traction. Here, a smaller student model is trained to mimic the behavior of a larger teacher model, transferring its knowledge while reducing inference costs. This is particularly vital for deploying AI on edge devices with limited resources. Section 4. Challenges and the road ahead. Despite these advances, challenges remain. Issues like catastrophic forgetting, where models lose previously learned information when trained on new data, still plague continual learning. Meanwhile, interpretability remains a black box. Even the most powerful models often lack transparency in their decision-making. Researchers are tackling these problems with methods like neural architecture search, NAS, and attention visualization tools, but the path forward is far from clear. Yet the pace of innovation is accelerating. From quantum machine learning to neuromorphic computing, the next frontier is already emerging. The key takeaway: AI isn't just about bigger models. It's about smarter, more efficient, and more ethical systems that align with human values. So what does this mean for you? Whether you're a developer, researcher, or curious learner, the tools and techniques we've discussed are shaping the future of technology. Stay informed, experiment with frameworks like PyTorch or TensorFlow, and keep pushing the boundaries of what's possible. The AI revolution isn't just coming, it's here.